Oh no, I've got the lights off. I just realized that. I see it start up and I'm like, the lights are off. Gotta turn on the lights now. The lights are off. Back to the old days with no lights. No lights in the studio. That's, whoop. So many wires and things in the studio. There we go. Now we got lights. We're knocking over stuff. Oh my gosh. So many things. Let's put the camera over here. Lights, better, worse. You never know. Camera goes over there. Should try to figure out how to make the camera even better. Ah, lights. Anyone's here. Getting things fixed up over here. Trying to fix up the stuff. Here in the chat, feel free to say hi. Nice final submission. Hey, Sweezy, what do you want to do, Sweezy? What do you want to work on? Here, it just goes crazy on that one side. When is the Stat Tool 1 final? Next Tuesday, right? Let me go look at the syllabus. Need to go put in, May the 4th be with you. We just passed the 4th. Exam 3, May 14th at 3:15. So, May 14th at 3:15. May 14th. I'm fixing up some dates. Fixing all the dates. Any help with the stats homework question? I gotta jump. Yeah, which one? Let me know which one. We'll do it. Update. Updating things as we speak right now. It is updated. Like that's. Oh, is that on? Which one shall we do? Getting the homework up and going. Okay, I think that's updated now. So many things. So many things. Need help with the stat homework question for getting it to jump. Which one though? Let's do it. How's it start? Is it the children and adult serial one? Chapter 17, children and adult serial? Is it chapter 19 with chi-squared? Chapter 19 chi-squared? Which one is it? We'll take a look. And logged into everything. Which one is it? Mewbot's not even awake. Was he awake this whole time? Chapter 19 chi-squared. Let's do the chapter 19 chi-squared. Okay. The homework questions? I might do the full homework then. Do the full homework. Might do reverse order then. Maybe it's like one of the last ones. Okay, here we go. Do you want to do the full homework or go to like a question number 5 or something? Which one do you want to do, Sweezy? Your call. Chapter, like, do you just want to do full homework, walk through? You tell me what to do, and I will do whatever we're going to do. Which one should we do? Should we walk through the full thing? I'm tired today for some reason. Got up early. Had more work. You pick. Logged in. Can we do 1, 2, and 6? Yeah. Should we just, maybe we'll do the full thing. I'll start with 1, 2, and 6. I've got question 1 already up. Logging in via 2-factor. Okay, so let's mark this in the video. Chapter 19, homework. Here we go. Chapter 1, chapter 19. You got it, Sweezy. 19, homework, question 1. Let's do it. Here I go to the main screen. Okay, so this is the chi-squared test of independence. When you do the chi-squared test of independence, you're working with 2 categorical variables, which is the condition count data. So there's 4 conditions. Condition 1, randomly select the observations. Condition 2, less than 10% of the population is sampled, and then we pause. And the next 2 conditions are based on the type of data we're working with. So condition 3, there is no real order to these, but I like to do them in a certain order to remember them. Condition 3 is expected cell counts have to be greater than 5. We might have to check that on one of these. And condition 4 is going to be count data, which means 2 categorical variables. By literally having a chi-squared test, you are literally doing the count data. And you can see it right here because this is testing whether or not where somebody got hit, whether it's the body, the head, the neck, which is the body, and the limbs are also the body. I think they mean the chest area right there. During a war, whether the injury was fatal or not fatal. Now you'd look at these and say these are numbers, but they are count data, which means they're the bivariate combination of two categorical variables. This is bivariate categorical data. Was it lethal? Yes, no. Where were they hit? Body, neck, head, limbs. Those are all categories. So conditions are met as far as we can tell right now, at least when it comes to the data. And is it randomly sampled? Yeah, probably not. The null hypothesis here, my favorite way to write it. So you'll oftentimes see me do this right here when I write out a null hypothesis, is I'll just go right here. And this is the way to remember the null. It's the chi-squared test of independence. So you just go right here and you say independent. Now I can't promise you my Pearson's always going to give you one that lines up perfectly with this, but you could say where somebody gets injured is independent of it being lethal. The alternative, you can say not independent, but that also means associated, as in knowing where somebody got injured would give you information about whether or not it was lethal. If you look right here, the less likely to be fatal ones would be the limbs, with more people surviving limbs, where the head and neck, very bad place to get injured. So it looks like there is some association just by looking at the data, which means we're probably going to reject the null. We'll find out more as we do the question. So the null hypothesis right here is going to be that they're independent, and the alternative not independent. My favorite way to write it. Do realize that there are synonymous things with not independent, like associated. You have to think, what does not independent mean? Not independent means knowing one would tell you something about the other. Independent means if you know one, it tells you nothing about the other. So let's check that answer. Got it right. So now we have to find the expected cell counts. Now you can do each of these by hand, which I do suggest doing some of this work by hand. The expected cell counts are via the formula. This is a very formulaic chapter. Expected cell counts are going to be row total times column total over grand total equals expected. So what you do when you're solving this, you go to the row total, you circle it. You go to the column total, you circle it. You do the grand total, and that would be the expected cell count for this cell. I highly suggest, we might put it into JMP because it's going to require a bit more work, but know how to solve this. We put questions like this on the test that ask you to solve it. So know how to solve it, know how to plug in and do 69 times 126 over 151, row total times column total over grand total. Know how to do that, plug it into the calculator and get it right every time. We are probably going to put this into JMP. It'll just make things quicker solving it in JMP. There we go. That is the, and do be careful. I think this one, it does keep it in the right order. There's one of these that messes it up. Okay. So to put this data into JMP and make our lives easier, we're going to click on the table of injuries and go here and go to copy to clipboard. So make sure you click the button over there on the left and then click here and then go copy to clipboard, and then it can hit Control C or Command C. Control C or Command C. Now we're going to go over here to JMP. Make sure we don't have anything open in JMP right now. Bike data is the only thing open. We're going to go into JMP right here and go to File, New, Data Table. File, New, Data Table. Under File, New, Data Table, you're going to go here and go to Edit, Paste with Column Names. If you don't paste with column names, you're going to have a bad time. So it should look like this right now with 2 blue ones and 1 red one. And we do have to fix this up a little bit right here. I think so, because all of a sudden my brain's like, how do I do it again? Oh, because this right here, we have to stack it, I believe. Yeah, we are going to have to stack it. So let's go here and go to Tables. And under Tables, go to Stack. Make sure they're red, blue, blue. And what I mean by this is red, blue, blue. Start over. If you don't have this, don't try to fix it. Start over and repeat the steps and make sure to paste with column names. Tables, stack. Tables, stack. Click only the blue columns. Click, 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 click. And you should see a new data table over here on the right. After clicking both blue columns, it should look like this with the counts of the data and the 2 variables over here on the left. We're going to go ahead and click OK, and we get our final data table, and we are ready to analyze the data. So now we have the data. So make sure you're here with 2 red columns and a blue column now. And you can relabel this as site of injury. You can relabel this as outcome. What I did right there is I double clicked it, and it lets you change the column name. You don't have to do that. It just kind of helps with looking at the data. So now we're going to go here and go to Analyze, Fit Y by X. Analyze, fit y by x. Do you remember you can pause the video at any time? You can also rewind, even live. Analyze fit y by x. With analyze fit y by x, we're going to put in here the site outcome, or the outcome as the y. That makes sense. Why do you have certain outcomes? Well, maybe the site of injury explains it. So kind of think of this when you're talking about it as, does site of injury explain why there is a certain outcome? And then very important, the data has to go into here. So make sure you have everything looking like this. I'll pause right here for a moment. And if you have all this right there, you can go ahead and click OK. And the colors matter. If it's not red, red, blue, there's going to be a problem. Let's go ahead and click OK. And we get the analysis right here with the chi-squared test of independence. And you can see, as we saw earlier, that when they're hitting the limb, the outcome is less fatal. The not fatal is much higher. And the most fatal spot was the head and the neck. And now we get to the contingency table right here. With the contingency table, yeah, there's so many steps, right, Sweezy? It's very tricky. I understand why students might not have it. We're going to click the red arrow. We're going to delete a lot of these extra things just by unchecking them. Then we're only going to have checked expected and cell chi-squareds. That's usually the only things we analyze. So once again, I'll show what I have checked and only checked right here. I only have those checked. And you can see the expected, which we have the first one, the 57.57. You should be able to find all of these numbers right here. There is a trick, because you could just find 2 of these with the 2 degrees of freedom of this table and then get the remaining ones. So I should have done that trick, but it's an advanced trick to kind of understand and solve these problems better, because what you can do is 57.58. If you go here to the total over here on the right side, well, if you know 57.58, you could take 69 and minus from that, and this would be the other expected cell count. That's not the formula for it. It's just a trick to get it, because the expecteds also have to add to the totals. You notice how 69 is right here, and 63 plus 60 plus 6, excuse me, is 69. Oops, you can't see that. 63 plus 6 is 69. Well, 57.58 plus 11.42 is that. You'd need one more. You'd need 39.22 right here. And then you could technically take right here, we'll put it on the screen. The answers are on the screen. We're just kind of showing how to get this on the test. There's the classic formula, row total times column total over grand total. But then there's also, because of the degrees of freedom, you could take 126, which is the total of this column, and subtract from it the 2 other ones. And check it out, we are going to get the remaining one right here, 29.2. And once you have 29.2, you could say, well, 29.2 plus something has to be 35. So you could go 35 minus. Once again, these are not the formulas. It's just a trick to getting them. The actual formula, if you want to solve it on the test, would be row total times column total, or row total times column total over grand total. On the test, preferably you would do 35 times 25 over 151, and it's 5.8, or, well, we rounded it, and there's the answer. Is this making sense, Sweezy? There's lots of ways to get these answers. 7.78 is the expected for this cell right here. Knowing how to get them is the important part. That way you can solve the expected cell counts. So now we get to the cell chi-squared. Great job, Sweezy. The cell chi-squareds are going to be the individual discrepancies of the observed minus expected squared for each cell. So if you take this right here, oh, it's Alexa making that noise. I'm hearing noises on my phone every once in a while, and it's like Alexa beeping into me. Don't do that. So if you look at this cell right here, it has a very large discrepancy. And what we're going to do right here is we're going to take observed minus expected and square that quantity and do that over expected. And that will give us a cell chi-squared. A cell chi-squared is a metric of discrepancy for a cell. That'd be a cell chi-squared. So we'll write cell below it right here. So we take the observed of 18 minus the expected of 5.8 and do it, and we square that quantity and do it over the expected of 5.8. And so then we solve this out. So let's put this over here. And observed minus expected is going to be the discrepancy. And now we are going to square this and divide by the 5.8, and it's 25.66. And we might not have carried all the decimals. Jump will carry even more in the background. Oh, I did round this to 5.8. So if you carry more decimals, it's 25.7. Now, what you would do if you're doing this by hand is you would find all the cell chi-squareds. Notice how this bottom row right here is the cell chi-squareds. You'd find all of them, and then you'd take all of these and sum them up. You would sum up all the cell chi-squareds. So 0.5 plus 2.5 is 3, plus 1 is 4, plus the 5 right there, 5.9 is 10, that's 15, that's 40, and then we go look at the output, and right here you'll take a look. The Pearson chi-squared test statistic is about 40. Once again, we're not doing this by hand, but if we were to add up all the individual cell chi-squareds, all these numbers highlighted in yellow, you would get the Pearson chi-squared test statistic. And that's 40, which is a very large one. And why do we know it's large? Well, because it has a very small p-value indicating statistical significance. And you notice when I hover over it, it says that. So it's basically 41 with a p-value close to 0. And we see right here the degrees of freedom are 2 because, and this is one of my favorite things that people practice, I say to people, this is a 3 by 2. Drop each finger, 2 times 1, 2 degrees of freedom. It also goes to the trick of how we were able to figure out the expecteds by just finding 2, because everything else is a forced choice, which kind of goes how the degrees of freedom work for this problem. So 40.9798 to 2 decimals right here. And I would have guessed a p-value of basically 0 on this one, because degrees of freedom are 2, because it's a 3 by 2. And the p-value is basically 0. It's so small that it's ridiculously small. If we found it, I could use R to find it, but it's got very, very small. Lastly, we want to do this without reading theirs. We want to say, I reject the null hypothesis with a p-value of basically 0, which is less than my alpha of 0.05. This is strong evidence against my null hypothesis and for my alternative. The null was that the two injury sites, or the injury site and the outcome, are independent. The alternative is that injury site and the outcome of it are not independent. That is what I now believe. So we reject a null with an alpha level of 0.05, usual alpha level. This, we can conclude that they are not independent. Try saying it yourself. That's where the real practice comes in. And that is one of the best problems you can do. That problem right there, if you know the steps of it right there and what you're solving and what it means, that was almost the whole chapter except for conditions. So really amazing problem right there. Sweezy, is it making more sense? This one might also be a review. But that problem right there is pretty much the whole chapter. This chapter is not as bad. I think it's a shorter chapter. It's very repetitive because we're doing statistical tests. So it's another statistical test. So now we have the same sort of thing. This is another same war story. So we have the null hypothesis for this one. Once again, we just did this one. Check out the last one where I went a little slower. The null hypothesis, you want to write independent between these. Everything just, I love hearing that. Throw some points, Sweezy, right there. Once again, ooh, Sweezy, how many degrees of freedom on this one? This is a 3 by 3. I like these questions on the test. This is a 3 by 3. Remember the trick about 3 by 3? I feel like Luke with the force, and man, may the fourth be with you. Very true on this one. How many degrees of freedom on this? There's another trick. I'm writing the null. A trick with the degrees of freedom. You just do that, and then you can see the degrees of freedom. Yeah, boom, Sweezy knows it. There you go. Just delete one row, delete one column, and that's what we're saying. We're already finding things that the question hasn't asked for, but it's a 3 by 3. Drop a finger. 2 times 2, 4. And be careful. Sometimes people will count the margins. Exactly. Don't count the margins. That's a common mistake. People say, but Brian, it's a 4 by 4. And I'm like, those are the totals. Those are not answers to the questions. There are 3 categories to injury site and 3 categories to what they were injured with. So make sure to do that. Be very careful. The more you practice it, the more you get it right. You'll remember not to use the total columns. So the null is that they're independent. The alternative is that they're not independent. Do realize that you can do not independent, also could be called associated. I'd like you to do one of these by hand to show you can do it, because if you go right here to the data, you should be able to get a expected value by hand. You should be able to do that. The test will have you do that. Remember, the formula is row total times column total over grand total. You do get a formula sheet. Good morning, Margaret. Good to see you there. But I usually see the Paul investigate. Yeah, I think so. I bet we'll be doing that one here shortly. You got it. And there it is right there. 13 times 64 over 135. 6.16 right there, rounded to 2 decimals. You know what? Let's do this full one by hand for a moment here. And then we do the next one. This is what you'd be doing on the test. We'll put this into jump here in a moment. And we'll do one more, and then we'll show the trick of how to get another one. So now this one, and notice where it crosses in on it. That's the key, is that we're solving for that value. That is the count, which is how many are observed. So we observe 3, but we would expect by random chance 5.21. 1, 2. Reverse, right? No, 2, 1. And then if we take those, we can go right here. Oh my gosh. Let's go right here, and there we go. Got a lot of screens open. And we can subtract from the grand total. This is the trick I do if you wanted to double check your work. You could take from 64 and do 64 minus 6.16 minus 5.21, and this should be the answer for this one. Now let's go and check our work with jump and get the remaining answers. Know how to get some of those by hand. So to get this into jump, we're going to go right here and go to the blue box and click this here and go to copy to clipboard. Make sure to click all those buttons and then hit Control C or Command C and then click done to leave these areas. Now we're going to go here into jump and we're going to go to File, New Data Table. File, New Data Table. With File, New Data Table, you want to go to Edit, Paste with Column Names. I went a little quick right there. Edit, Paste with Column Names. Make sure when you look at this, it'll be red, blue, blue, blue. So red, blue, blue, blue. Now you want to go to Tables, Stack. Tables, Stack. And under Tables, Stack, you're going to click the blue columns. There you go. Make sure all 3 blue columns are right here. Table, Stack, and then click OK. Notice you have 2 categorical variables and then the count data over on the right. Click OK, and you should see red, red, blue, and you're good to go. You can double click the columns and call this object, whatever you want to call it, weapon, or let's call it weapon. Double click and call it weapon. You don't have to do this, but it makes it nice. And then you could say injury spot or spot. There we go. We have the weapon that was used and the spot that was injured and the counts of observations. Make sure they are red, red, blue, and then we have the data properly in jump, which means we can analyze it. Now that we have the ability to analyze the data, let's go to Analyze Fit Y by X. Under Analyze Fit Y by X, you're going to go right here and double click data and put it in frequency, or just drag and drop or something. There you go. Make sure right there. If you double click, it will go into the Y response. Do not put it there. I misspoke. We want to see if the weapon explains the spot of injury. Does weapon explain spot of injury? Make sure everything looks like the following. Spot is red and in Y, weapon is red and in X, and data is down here in frequency. Let's go ahead and click OK. So now we have our table, and does this look right? Let me see their data over here. Right. And yes, good, good, good. Sometimes they reverse it, body, head, neck, limb. We're good to go, I think. So now we're going to take the red arrow. With the red arrow, we're going to uncheck total, uncheck columns, uncheck row, go here and put expected, and we're going to put cell chi-squared. The second row is what we want with the 6.16, 5.21, 52.622, and that doesn't round. Got to be careful. Is it going to? I'll see if it counts me wrong on that. Some decimals got carried around and made small differences, so I wonder if that's going to cause a problem. Once again, you want these buttons checked right there. I'll zoom in just a little bit so you can see we have those 3 checked. We're going to put in the remaining values. I'm going to move it over here so I can see it and write it at the same time. 4.43 and 2.41 and 3.75 and 2.04 and 37.2 and 20.56. Is it going to tell me I'm wrong because of this one right here? That is the one I'm worried about. I used the trick to get it, and 52.62222. Is it going to tell me I'm wrong? The answer is nope. A little bit of leeway on these, tiny bit. I would have changed that. I just wanted to see how much leeway there was. I would have changed that. Now, the chi-squared of this can be found, and this is a good thing to know, by adding up all the cell chi-squareds. These are the theory things you need to know, is that the Pearson chi-squared test statistic, so write this down, the Pearson chi-squared test statistic is the sum of all the cell chi-squareds. So the cell chi-squareds are a metric of discrepancy between the observed and the expected. And so it's observed minus expected squared over expected. So if we take 0.0043, these are all the cell chi-squareds. I have only the cell chi-squareds showing right now. We take all these cell chi-squareds. This is what we used to have to do back in the day as we were doing it by hand. So it's important to know what you're doing. Why am I doing this? A long way. And there we go. And that value is the value right down here at the bottom of the screen. There it is. We got exactly that value to the decimal, 6.019. We're not doing the likelihood ratio, which is a different type of test. It can be used to get the p-value. And this one is not so extreme. A larger chi-squared leads to a smaller p-value. It does depend on the degrees of freedom to tell us the shape of the chi-squared. But we're going to take this chi-squared value right here, the sum of all the cell chi-squareds, and that is the chi-squared test statistic to 2 decimals. And then we're going to put in the p-value. Let's see if we remember it. How many degrees of freedom? Remember, 3 by 3, drop 1 finger, 2 times 2, 4 degrees of freedom. And what do we mean by 3 by 3? There's 3 answers to where someone gets injured, and there's 3 answers to where somebody, what object was used or weapon was used. And then also what we have right here is rows minus 1 times columns minus 1, 2 times 2, 4 degrees of freedom. And the degrees of freedom show you the shape of the chi-squared. So it's very important to know why we get degrees of freedom. The chi-squared is a right-skewed distribution. So if you go over here to the chi-squared distribution, it's right-skewed. And as you add more degrees of freedom, it becomes more normal. So if you don't know the degrees of freedom, you don't know the shape of it. And there's infinitely many chi-squared distributions. Interestingly enough, you'll notice the center of this distribution, if we zoom in on it, the center is right about at, oh no, wait, there, 147, there we go, that's really good. Oh, moved it. 150, the center of the chi-squared is actually around the degrees of freedom. So you notice right here where it says 150 would be at the center, and that's where the degrees of freedom are at. That's only when it has a large amount of degrees of freedom. Usually after about, I think, 60 degrees of freedom, we can use the chi-squared normal approximation. So you'll notice the center's there about 60 and it becomes normal. But that does not apply in, like, for a chi-squared right now we have with 4 degrees of freedom. It's very, very right skew distribution. Still the center over there, but that's just fun facts about data. P-value, I think it was 0.97. I think it was. Yes, it was. I remember, I could see it. Yeah, I'll round it up. 0.97197. I didn't say the 1. That's a very, very high p-value. When the p-value is high, we just let the null fly. So try doing it without looking at it. I was analyzing if there was a relationship, that's what it means for things to be independent. Well, they wouldn't have a relationship. I'm analyzing whether there was a relationship between the weapon used and where people got injured. My null hypothesis was that they are independent, meaning that knowing where someone got injured would tell you nothing about what weapon injured them. My chi-squared test statistic came out rather small, and I plotted it on a chi-squared distribution with 4 degrees of freedom. When plotting it on the chi-squared distribution with 4 degrees of freedom, it was like 6 point something, wasn't it? I got a p-value that was very large. My p-value, which was very large right here, has me not rejecting the null. My p-value, which is very large, has me not reject the null hypothesis. So since I do not reject the null, I do not have evidence for the alternative, and I do not conclude that there is a relationship or they are not independent. So I fail to reject the null at the alpha level 0.05. I do not conclude that they are not independent right there. Once again, know how to say that, know how to write that. That's the hardest part for people a lot of times. What does this all mean? It means that the differences we saw here, and let's take a look at those two. Here's one more likely by random chance. I know there's big differences there, but that's a smaller sample size. Where on the previous one, which it looks like I closed, we saw bigger differences which were less likely by random chance. So here we are, this is that data, here we go, the other data. Analyze fit y by x, says outcome explained by site from the data, and here we are here. So we have the first test we did and the second test. The first test had large differences which were unlikely by random chance. We know this because of the very small p-value down there at the bottom. The second test had differences which are likely by random chance. And probably a lot of the differences are coming from this over here that are making it unlikely by random chance that people hitting the limbs were more likely to survive. These differences right here, that ground and rock were more likely to injure head and neck. And you'll notice it's much higher percentage, 63% of the ground rock injuries occurred to the head neck. Well, it looks like these differences are probably just random chance. Why? Because the p-value is high. So we do not think there's an association between the two variables on the right, but we do think there's an association between the lethality of an injury and where you're injured. What was used against somebody on that side of the body does not look to be associated. It looks to be independent, that you could just get hit with a sword anywhere. I don't know, it doesn't tell you anything if we know what you got hit with. We don't know where you got hit, probably. It doesn't give us information. Okay. I think questions 3 through 5 are probably going to be quick right here. They're probably easier questions. We haven't even done the conditions, though. Well, we kind of did them. I should have mentioned it, how we had at least 5 expected cell counts. So let's see. Chapter 19. This might be homework questions 3 through 5. Let's find out. Suppose we want to conduct a test of independence and end up rejecting the null. It means we found a low p-value, a p-value less than 0.05. Which of these following conclusions is appropriate? I think I do have qualms with this one. I'm not going to look at the answers. If we end up rejecting the null, we have evidence to the alternative. We think the two variables are associated now. I'm going to say there is an association. You should say we have evidence of an association. That's better. When variables fail the test for independence, they're considered to be... Wording on this one, I might say we need to replace this. I don't like the wording. When we reject the null for the chi-squared test of independence, we have evidence of an association. Yeah, no worries. Good job, Sweezy, right there. So I wouldn't phrase it the way they're phrasing it. I would say when we reject the null hypothesis for the chi-squared test of independence, we have evidence of an association, or we believe they are associated. That's fine to say too. They're believed to be associated. We have good reason to believe they're associated. We don't know why. Good reason. Yes. Okay, I think this is going to be the questions right here. Okay. For the chi-squared test of independence procedures, the sample size assumption is checked by the what? So kind of, sort of, two of these just don't apply. So if you know your conditions, you can get it right. It deals with the residuals and how if we have too small of these, it's going to cause problems and we can't really rely on them. Just if people are wondering, I might show it. If you have very small expected cell counts, take a look at what happens here. If you remember how the chi-squared test of independence is run, we have observed, which is what you see. Expected, which is what is expected by random chance, with the formula row total times column total over grand total. And the observed is equal to observed values. It's just what you see in the cells. And then we get the cell chi-squareds, and the cell chi-squareds are going to be the observed minus expected squared over the expected. And it's a metric of discrepancy that's standardized. Last but not least, we have the Pearson chi-squared, which is the whole point of the test. The Pearson chi-squared is the sum of all the cell chi-squareds. So if you take all the cell chi-squareds and add them, you get the Pearson chi-squared. What you'll see right here is with this observed and expected, so there's the observed, expected. If you run the test and you have a very small expected, you have an expected of like 1 and you have an observed of 11, then you do the following right here. You do observed minus expected squared over expected, and we'll write small right here. So this would be a problem. We put it in red right there. And then let's look at the difference over here, because now we have a large one. So in both instances here, I'm going to make a difference of 10. So now we'll go here and we'll do 110 minus 100 over 100. And I just want you to see where these things are located. This would be the expected of the test. We're just making up a theoretical fake test right here if we were running data. And I want you to see the differences of what happens here. Both of these have a difference of 10. But in the first test, we get 10 squared over 1, which is equal to 100. In the second test, we get 10 squared, which is 100 over 100, and that is going to be equal to 1. So notice right here, when we have a large chi-squared expected value or large expected value, these differences are not as big. So the problem is when you have these small expected values right here, small expected values, you oftentimes get large chi-squared test statistics where there's not really big differences. So the test is kind of biased towards rejecting the null when you have very small expected values. So what we say is you have to have at least 5 expected before the test can be considered reliable and not kind of giving you a type 1 error, which is a false positive. So kind of looping in some other ideas right here. This is why we do it. The test isn't really reliable. The residuals, like the difference between that, the observed and the expected, because that's what a residual is. Like expected is what we would predict and observed is what we see. So actual minus predicted again. Literally, you can think of this formula. Is the top of it is a residual actual minus predicted. The reason we square it is because residuals could be positive or negative. And then you go right here over the predicted to standardize it in context of the problem. I wouldn't write it that way as actual minus predicted, but it really is, because actual is what you observe and predicted is what is expected. And we talked about this in my class, how the formula for this is actually just the multiplication formula assuming independence. So a lot of topics converge right here. You've got regression, you've got chapter 10. So like literally regression, literally chapter 10 with probability. And yeah, that's why I love stats, is because it's a very cohesive discipline where you'll be like, wait a minute, that's just a residual up top. I'm just looking at a difference between what I observe and what I expect. And so we have the expected cell frequency. Now, do remember that success failure is for categorical data. So we have categorical data for success failure. We need at least 10 successes, at least 10 failures checked by for confidence intervals, NP hat and Q hat, and are greater than or equal to 10 for test, and P naught and Q naught are greater than or equal to 10. The nearly normal also includes the large enough n condition. Could go into more detail on that on a question that covers the nearly normal for quantitative data for the 1 sample t and the 2 sample t. Little mini lecture right there on a multiple choice easy question. The next one says the degrees of freedom of the chi-squared test depends on what? So do remember we hold up our hand and we say, Brian, this is a 3 by 3. So degrees of freedom, we drop one finger on the rows and on the columns. 2 by 2, 4 degrees of freedom, and it would be the dimensions of the table, the rows and the columns. The formula is rows minus 1 times columns minus 1. See if you can sit down and write a lot of the things I'm writing out right here. If you remember, observed is what you see. The expected is the row total times the column total over grand total. Cell chi-squareds are going to be observed minus expected squared over expected. Pearson chi-squared test statistic is the sum of all the cell chi-squareds. And the degrees of freedom for the chi-squared, be careful, this is a chi-squared degrees of freedom. So degrees of freedom for the chi-squared test are rows minus 1 times columns minus 1. And you just go to your table a lot of times and delete one row, delete one column. So if it's a 2 by 2, there is 1 degree of freedom right here. This would be the 1 degree of freedom. I like thinking about it like a Sudoku puzzle, because if you were to go right here and put numbers like 80, 20, oh, that looks like 70, sure, it can be 70, 50, 100. And then we just choose a number at random like 20. So 20 is chosen at random. And then now take a look, 60 has to go there. Ooh, no. We have to change it because we broke it. We broke the Sudoku. That's why you gotta be careful. 90, 60, there we go. Now I think it'll work. And this would be 70, wow, there we go. Every number was a forced choice. It's just, you say, well, Brian, you say you could pick any number. Well, it has to work within the constraints of the table. But the 1 degree of freedom on this 2 by 2 was used up. And then every other number is a forced choice. And we can't assign any more values. And if you run out of degrees of freedom, you can't estimate residuals and you can't run your test. And that's the only reason they matter, or the shape of the distribution. Last question right here, a little bit longer of one, the early term, preterm question. That's a good little section right there. I'm ready. I like it. Here we go, homework, question 6. Okay. So we can take this data and put it into JUMP. Let's go ahead and grab it right here. We're gonna grab this data, put into jump. I think Margaret wants, or Maggie wants, the other one, the liberal conservative. Copy to clipboard right here. And then we're going to hit Control C, Command C. Once again, the steps were click this button here, copy to clipboard, Control C, Command C. Now we're going to go over here to jump. We're going to click on anywhere in jump, and we're going to go to File, New Data Table. Now, did you know you can click on a lot of programs, Control or Command N, and open up a new instance? So Control or Command N opens up a new instance, and we're good to go. We can go here to Edit, Paste with column names. It also shows you the shortcut there for Edit, Paste with column names, which is going to be Control-Shift-V. Now be careful, make sure it looks the following way with red, blue, blue. You can use the shortcuts if you want. They're slightly different on a Mac, but I do love using the shortcuts, but I'm only showing you this now because I want you to follow along, but check out shortcuts. They make life easier. You just go new, there we go, paste with column names. That quick when you want to do it. Compare that to clicking through the buttons. Shortcuts are better. And now we have to stack the data. I wish there was a shortcut for that. Might be. No, there's not. Table stack. Table stack. Under table stack, you're going to double click both the blue columns. Click, 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 click. And with both blue columns clicked, you're going to then click OK. So we've double clicked the blue columns, and now we're going to click OK. Boop. Now we have our data ready to analyze. So you can double click and call this age group. You don't have to spell it correctly. This is going to be outcome. It just makes the data look nicer. You should see red, red, blue. So red, red, blue. We can deselect the data. And here we are, red, red, blue. Ready to go with the data. Analyze. Fit Y by X. Analyze. Fit Y by X. Under Analyze, fit Y by X, you're going to then take and see the data goes into frequency. That's the counts of the observation, the literal count data. Now we have outcome, which is what we want to analyze, which will be the first column, the second column for you right there. We're going to put that in the Y variable of interest because we want to know why are there certain outcomes, and maybe age group explains. Remember, when we do the null, we can just put independent between these. Is someone's age group independent of their outcome or not associated? The alternative would be is age group associated with or not independent of outcome. You only need to write one of those, but make sure to understand what we're saying when we say the null. Don't just repeat it, understand it. We're going to click OK now. And I can tell you, Sweezy, if you've been following along, the p-value for this should be very, very what? The p-value for this should be very, very what? Looking at this visually, I can tell you the p-value. I could guess it. It's a hard one to guess, but I know for certain it's going to be a certain thing. Well, I can't say for certain because sample sizes do come into play, but I have a hunch it's going to be very, what do you think, high or low? Boom, Sweezy. I like that because they look independent, right? Sweezy, wow, great job. Really good job right there, Sweezy. Look right here, high p-value. I thought it was going to be closer to 0.8. I would have been wrong. But the chi-squared is low, meaning we have a small discrepancy between our observed and expected from the cell chi-squareds. And so if you're following along with the other examples, seeing where there are bigger gaps, lower p-value, the highest p-value would be if they're flat across, and this looks more like flat across. You can't know the p-value exactly from that, but they look pretty flat, and the p-value thus would seem pretty high because the differences are likely by random chance. We're going to click right here and go to remove everything but count. And go right here, go to expected, and then cell chi-squareds. There we go. Make sure you have this. We'll take a look at the data here in a moment. We should pretty much have all of the results now. Once we do this, we have all the jump output we need to answer all the questions. Then we just have to know how to analyze it. So we have everything good to go. Let's go back here to the question itself and see what it says. What is the null hypothesis? It's that they're independent. They're not associated. So they're independent, and the alternative is that they are not independent. You could say dependent. That's fine. A lot of ways to say it. Chi-squared test statistic was very small relative to its distribution. The chi-squared test statistic is the Pearson chi-squared right here, 2.242. Got to do that many decimals. 2.242. That's the chi-squared test statistic found under the test right there. Make sure you do the Pearson chi-squared test statistic. Pearson, and then the p-value is one associated. Pearson has your p-value. Pearson chi-squared test statistic. So 0.538. Go. Got it. and the p-value is ridiculously high. Once again, don't try to read their answers. I know it's easier to read their answers and then think which one's right, but you want to say it yourself. Be like, well, my p-value was ridiculously high for this. A p-value of 0.5234, whatever it was, or 0.524 is way higher than 0.05, which my usual alpha level is. I do not reject the null. I believe that someone's age group and the outcome of when they have their baby is completely independent. I still believe that. I did not have strong evidence or any evidence at all for my alternative hypothesis. I did not have any evidence for my alternative hypothesis. So the p-value is greater than the alpha level. There is insufficient evidence to reject the null. Once again, if you notice what I'm noticing immediately, p-value greater than alpha, boom, that's a fact. That means you do not have evidence for the alternative. So when you go here, there's insufficient evidence to reject the null and conclude that they're not independent. So my p-value is high, let the null fly, do not reject the null. Once again, a really good question. This homework is excellent. It didn't have the conditions really well. Okay. Other than having you understand the conditions, random, 10%, expected cell count, and then last but not least, count data, which means two categorical variables, which by virtue of this being what the outcome category and then the age group category. But this is a very good chapter that, especially the homework right here, really good stuff. I guess we might do a lot of the quiz. What questions do people have? I need a fourth cup of coffee. Need some white chocolate, fourth cup of coffee. Just all so much. Coffee, coffee, coffee. In the words of Philip J. Fry, coffee, 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 coffee. Coffee. I haven't started, so any help on the quiz would help. You got it. I can feel it. I can feel people being ready for the semester to end. Like as we go further along, like he just gets so far along. Let's get the homework quiz. Oh, quiz only has. Are you serious? Oh, quiz only has 5 questions. Well, I'll be. Might be able to do every single question. Well, this one's a repeat. Only 4 questions you get? Oh my gosh. We delete questions on this? This might be one of the last few ones right here. Hey. Sweezy, you're like one of the only people here, but I like it. More points, Sweezy. Let's do the political one. Poll investigated. They added like, there's small changes to these every once in a while that I see, and I'm like, really? Really? Okay, let's go check this out. There we go. So the quiz is very similar to the homework. There's actually just, frankly, a lot of repeat questions if you ask me. And this one is not a repeat question. And let's first check our conditions on it. So finish it strong. I like that, Squeezy. So the conditions are for the chi-square test of independence. Condition 1 is random. We randomly collect these people. Condition 2 is less than 10%. Are the people less than 10% of the total population? Condition 3 is we're going to pause right there because we get different conditions when we get to the end of this. Condition 3 is going to be the expected cell counts are greater than 5. So we'll find the expecteds here in a moment, see if they're greater than 5. And condition 4 is going to be count data, which it could be condition 1. You could just call that condition 1 because you have to have count data to do the test. So one thing I love to do is do the easy things first. If you're writing the null and alternative, you just want to put the word independent between them. You can see I've already done it. Oh, that's where I wrote row total times column total over grand total. So if you're writing your null and alternative, you go right here to the test itself, and you just write the word independent. And that's the null hypothesis, that the region someone in is independent of their political identity. And it looks kind of independent, and the sample sizes look to be a little bit similar. More Republicans in the north right here, according to this data, and a little more independents in the south. We'll see if these differences are likely by random chance or not likely by random chance. And so the null hypothesis would be that they're independent. Oh my gosh, do we literally have all these stay independent, not independent? You could also have not independent right here be associated, because there's many ways to say not independent, like dependent, associated, related. Words for independent would be not associated, not related, and not dependent. So there are other ways to phrase this, but I prefer, it's actually all been my preferred method today of saying something is independent, X and Y are independent, and then the alternative would be X and Y are not independent. That's got that one. Immediately we jump to the chi-squared value. Well, these differences look small to me. I'm gonna take guesses and see if I get it. Those differences look small, so 4.123. P-value would be a little bit larger. Chi-squared's over to the right, so 0.6432, sure. And then I failed to reject the null. There's not evidence that they are not independent. And submit, oh wait, check answers. I'm gonna get it wrong. I'm gonna get this wrong. 50! I missed the, so you got a 50 on that, just doing that right there. But I also saw the differences were small and likely due to random chance, meaning high p-value, which means not too large of a chi-squared. So I got those two wrong, but we're going to solve the answers. I'm going to take a moment right here. Oh man, I would have, if I had gotten, I could check. So Sweezy, if we're doing this by hand, and this question doesn't ask it, how many degrees of freedom are on this? That would have been Hackerman for that. If I had gotten that, I would have, you just been like, oh, well, I've learned all the stats I need to know. How many degrees of freedom for this chi-squared over here? It's a 3 by 3, 4 degrees of freedom. So I can see if I guessed, like, so here it is, we'll go over here, and my p-value was even wrong. So if I know if I knew the chi-squared test statistic, I could get the p-value. I don't know the chi-squared test statistic though. So the good news is with this one, we don't have to enter in expected values. You can just go right here. So this is how to get the answers. Click copy to clipboard. With copy to clipboard, we're going to copy the data. We're going to hit Control C. And then we're going to hit the table over here and go to File, New, Data Table. File, New, Data Table. Under File, New Data Table, we're going to go to Edit, Paste with Column Names. Edit, Paste with Column Names. Under Edit, Paste with Column Names, we're now going to go to Tables, Stack. Tables, Stack. With Tables Stack, we're now going to double click the blue columns. And now we're going to click OK. So now click OK. And now you'll see your final table with red, red, blue. Double click this if you want, call it region. Make the data nice. That can be called political label, and then data should be red, red, blue, red, red, blue. And now let's go ahead and analyze fit y by x. With analyze fit y by x right here, we're going to see if somebody's region explains their label, and don't forget to put the data in the frequency. Very common error right there, not to have the data in the frequency. So you should see the following. Is label explained by someone's region? And then the data is trying to explain this. So let's go ahead and click OK. And look, high p-value probably, right? The reason we're thinking high p-value is the differences look to be by random chance because the mosaic plot mostly lines up. And if we were to get the observed and expected values, we can go right here. You can see the observed, as in 29 people were Northern Democrats. The chi-squared's even lower than I thought. 1.84. So 1.84. Is that enough? Yeah, I might not have done right. 4 decimals. Oh, wait. P-value can't be greater than 1. P-value can't be greater than 1. Okay, let me see. Ooh, can you not get that because of the... Oh, 3 decimals. There we go. Oh, really? No way. Wow, that last decimal, though. You can only be off by 1/10,000th. You really only need to be able to report a p-value to a third decimal. I got that last one wrong right there on the decimal. And this info comes right from the bottom of the graphic where the chi-squared test statistic is. The chi-squared test statistic being the Pearson chi-squared test statistic. The Pearson has your p-value and the p-value associated with it right there. So I'm actually blocking it. There it is, the chi-squared test statistic 1.84, which is the Pearson chi-squared test statistic. And then the probability greater than, p-values are probabilities. The probability of something as extreme or more extreme than this chi-squared test statistic is 0.7652. And what we could do is we could take the 1.84 and go here. And you'll notice this is the exact same p-value we have on the screen. So this is how the p-value is found by hand over here on the right, with the p-value now being displayed on the screen here with a chi-squared with 4 degrees of freedom. And there is the chi-squared test statistic. There are some of these I can figure out though, because if you get an extreme chi-squared test statistic or see extreme differences, like if we go back to this one right here, which I think has the extreme differences, notice how like not fatal occurs in limb, and this is a very large difference. So I could go down here and guess the p-value. P-value is probably about 0. What should we conclude? We reject the null, and this would mean we conclude that they are not independent. So, and then we would have to guess the other ones, which I'm gonna have no guess at. Well, we can basically get all these right. This, you'd have to work out the expected values. So expected values would have to work, and then they are independent is the null and not independent is the alternative. What I missed? I missed one? Chi-squared test statistic. Oh, how many degrees of freedom? I can do that one quick. 2 by 3, 2 degrees of freedom. So knowing how, and I'm not going to get the chi-squared. So the chi-squared is something like 45 or something, or big. Can't get a lot on this one, but the p-value is definitely 0. I have a quick question for you to help on the quiz. Suppose we conduct a test of independence and end up rejecting the null. Which of the following conclusions is appropriate? If you reject the null, you would have evidence that they are associated. So rejecting the null would be when your p-value is low. To reject the null, the p-value is low. You have evidence that the two things are associated. Low p-value means evidence for alternative. And right here, the two variables are not independent. It's kind of, sort of, I agree. This would better read, we reject the null, we have evidence for the alternative that the two variables have an association. Saying one variable depends on another, we don't know that there might be a lurking variable. I think that's what they might be going for. Answer B is like not as good of an answer. It's like answer C on mine is a better answer. Answer B is not a bad answer. Answer C is a better answer. And then the best answer would be when you reject the null, you have evidence of an association between the two variables. It's not that we know they are associated. Well, not that, see, I say no. I hate saying the word no. We have evidence of an association between X and Y. That'd be my best answer. If I were to write an answer to this by hand, I would say, yeah, it could be lurking variables. We don't know. Saying they depend is not wrong. I agree with you. I wouldn't like this on the test. I don't think that'd be fair on the test. Because it's like there's a decent, if it said select the best, it's one of those where it's like, well, it's a decent answer. I think we got a high p-value for this one, right? So they are independent as the null, and chi-squared test statistic we're not going to get. Well, we could try. 6.1. That would mean p-value is going to be kind of higher-ish. We're not going to get those. So with the p-value greater than alpha, since p-value is greater than or equal to the level of significance, there is insufficient evidence for alternative, 50%. And this one had small differences, 2, 3, 8, 1. Ooh, wait, sword. No, that's a difference right there. Sample sizes are small. I don't know. So the null is that they're independent, and that's a lot of values. I'm just having some fun. chi-squared test statistic. Let's go with, I'm only going to get it if it's a large chi-squared, which I don't think it is for this one. Degrees of freedom 4, because it's a 3x3. P-value is going to be larger-ish. And we would fail to reject the null. We do not conclude that they are not independent. Oh my gosh, we did get a low p-value. We reject the null, conclude that they are not independent. There we go. And is the p-value really this small? Did it go up? It did. The p-value 0. Oh man. So you did get a big difference. I was right when I looked at it. Which means the chi-squared is something large. Now that'd be cool if I got that right. Oh, how many degrees of freedom? It is still 4 degrees of freedom. Just have them all fallen. If you really wanted to get these right here, you would need to go in and put these into jump. So, and we just did this one earlier, so that's why I'm just having fun with these, because we already did these ones in the videos. I think this was question number 2 in the homework. So there's really only one new question. This shouldn't be that hard of a quiz, shouldn't be that hard of a homework. But what are your thoughts? This is the homework and the quiz here on everything. Right back to the main screen. Weekly opportunities. Take a look at some reports right here. Chapter 19 out of the way. Taking a look at some grades right here. Feeling good about it? I like chapter 19 a lot. Still getting another haircut. Here's getting all wacky. Wacky Wednesdays here. And at the question, how can we calculate our grades? So there is the, and this is for 201, right? There is the what if scenario in Canvas where you can enter in grades. So you can always click to the what if. Thank you, Daniel, for asking. There is the what if scenario. So check out the what if scenario. What if scenario will let you enter in whatever grades you want and do a what if analysis. You can do a what if analysis. So click the what if scenario and check out your grades there. Very, very important. Check that out. I would highly suggest it. Check out the what if analysis. What if analysis, it'll let you enter in grades, see what you have. You're welcome, Daniel. Good question right there. Oh, we have that here at UT. Some reports right here. Good stuff. What do we have? We have office hours later today. I'm just chilling right now. Reading over reports, taking a look at Look at the last report over here. Nice. A few minutes so far. Oh, we completed all the chi-squared. Might end early today. Might go on a walk, get some exercise. I'll have office hours here in a little bit. Until then, just got 100 years. Squeezy. Well, I'm gonna head out and go on a walk and relax. Into the semester, we have office hours coming up later here. Go take that walk. Thank you, Squeezy. Bye for now, everyone.